Good morning, students. Welcome back to School of Tomorrow on a Monday morning. It's time to get cracking, right? You're ready. This is a short video, and it's about not proving, which was done once by Dr. Bob Gray in my awareness, but showing through random generation of tetrahedrons that all tetrahedrons with IVM sphere center volumes have integer volume. So say that again. All tetrahedrons with IVM sphere center vertices is what I meant to say. So if the corners of your tetrahedron are all at the centers of IVM spheres, i.e. CCP spheres, right? We pack this arrangement going on out layer upon layer like this, and we fill space. And then we gradually pick, or we randomly pick any four of those vertices. Chances are any four balls anywhere, right? Any layer, any distance. Just pick four of them. Now, the chances that they're all on the same plane are pretty small, but it could be, in which case you don't have, well, I'd say you have zero volume in that case. So that's an integer too, but really, so the proof is, the claim is that every such tetrahedron of only IVM centers for vertices will have a whole number volume every time. So the Watermans are a special case of that. We talked about Waterman Polyhedra in the last few videos. You can go back and look. They are part of the Martian Math curriculum, as are quadrays. So we use quadrays to generate the FCC. This is taking from another Jupyter notebook, and this will all be in my open source archive, where we realize that the 12 corners of 12 around 1, i.e. this CCP packing of 12 around 1, we want to point in all 12 directions, and like our turtles in previous examples and random walks, if you look back a ways, we just want an arbitrary number of steps in each of those 12 directions. Because we know if we stick to those 12 directions, in other words, from every sphere center, those 12 directions are the 12 hops to neighboring sphere centers, right? There's always 12 around 1. So if we just take an arbitrary number of hops, like it's like randomly going through this thing and just randomly picking one of the 12 at every turn. Now I don't do it quite like that in the computations. By the way, for continuity with codesters, those of you who were following through the phasors discussion and how we were wrapping the unit circle using e to a complex number, just showing you again this can be done in a whole different set of tools. Still Python, but now that we're in a Jupyter notebook, not necessarily, right? Codesters, that was Python, but here in this context of Jupyter, the reason it's named that, JU for Julia, PY for Python, and R for R. So that's just a hint of all the different languages that you can put in these code cells. I happen to be using the Python ecosystem, so I'm taking full advantage of Unicode, and I'm showing how if you call this number 2pi, you call that tau, then you can recast your math and in terms of tau instead of 2pi. And there's a lot of people who favor that notation. You'll find them on YouTube, and it's not a bad idea. I have my own reasons for hoping that movement continues, because I think tau sometimes tries to mean phi, which some people pronounce phi, and it gets in the way. So if tau gets busy supporting 2pi, then it's less competition for phi or phi. Clears things up for me too, right? Okay, so we're back to what I'm really working on here. This is the actual demonstration, and I'm getting those 12 directions. So the 12 directions meaning the 12 hops to neighboring 12 around 1. And then I'm going to get what I call a linear combination of all those 12. It's like dipping my paintbrush into each of the 12 paint pots and getting an arbitrary amount of paint and mixing them all together. You could say it's like that. It's actually taking random numbers, and I'm allowing them to be up to 300 long and down to 0 long. So I'm going to scale these 12 vectors arbitrarily between 0 and 300 length. So think of that as the scalar length, which I'm picking at random. And then I'm saying I want like 200 of the first vector, 5 of the second vector, 203 of the third vector, 145 of the fourth vector, 18 of, and so on, right? So I arbitrarily pick amounts of each vector, amounts of each of these 12 vectors. And yes, some of them point in opposite directions, and so why, go that far one way and the other way, whatever, it doesn't matter. I just want 12 terms, one for each of these vectors. It's perfectly good linear algebra. There are other ways to do it. You could just do quadray, never mind. So then I need 4 of those arbitrary vectors. Once I've got linear combinations, I add them all up. Okay, it's like the turtle. I say do all those things, do those 12 things. Go those places, and you end up somewhere. In other words, it's a linear combination that ends up pointing bing to a specific ball somewhere in the universe. So let's actually run this now, okay? And then we're almost done. So I'm going to import the Q vector. Here's what you would often do in a talk, right? So say this is you in front of a group. You already know it works, so you're on the rails. You're not going to have one of those demos that for no good reason doesn't work because there's some stupid bug. If you've got your dependencies right, this is going to work okay. Okay, so it's a good demo format, and I've just cleared everything. So we don't see the results at this moment. Notice how all the outputs have, or all the inputs have no numbers because there's no corresponding outputs at this point. So to review Python a little bit, very familiar because other languages are similar, we can gradually populate the namespace with the stuff we're going to need. And notice it starts numbering from 1, not 0. This all inherits from the IPython notebook ecosystem and has been renamed Jupyter because it's more international, you could say. Jupyter meaning multiple computer languages. So JavaScript's very much a part of this, and the actual native format for storing Jupyter notebooks is a form of JSON. So there's my 12 so far my 12 vectors pointing in the directions of these spheres. Now these are what we call quadray coordinates, which are based on this tetrahedron and 4 tuple coordinate addresses for all points. So even though we're in so-called 3D space, we're using 4 numbers to designate where we're at, and they're always positive. And at least one is 0 because we're always in one of 4 quadrants, and one of the vectors isn't going to be needed in that quadrant. In other words, 3 vectors manage fine for each of the quadrants. So it's like 3 of them always step up to the plate and say, leave it to me, at least, right? And so forth. Now if it's at the very center, that's 0, 0, 0, 0, and you see the coordinates going around, and these are unit vectors, or we could say they are 2 because of radii of spheres at these 4 centers of the tetrahedron are CCP balls, right? And they have a radius of 1, we could say, or of 1/2, but of 1, in which case the edges are 2. So it's kind of an odd way to begin, you could say. It's like a caltrop instead of a jack, and the edges are what we care about, it seems like, more than the lengths of these guys, so that the actual quote-unquote basis vectors, as we sort of think of them, are not of whole number length either. They're not unit vectors, really. That's very strange. That's why it's part of Martian math. It's alien. So we're using those coordinates, and we're generating A, B, C, D. So let's keep going here. A, B, C, D are going to be so any ball, there's like, look at that. There's any position in space. D equals 0. So we didn't need the D direction. Well, that's always going to be one of them is 0, right? Because we're always in one of the quadrants, really. So you see they're all integers, right? So A, B, C, everything is an integer, which means that alone is not sufficient, but they're all integer combinations. They're linear combinations of those 12 directions. So every time I go any ball, I'm showing you the center of one of the balls. So the balls in the CCP all have integer coordinate addresses. That's a nice feature of Q-rays or quad rays. So we're ready to go. We just need 4 points at random, A, B, C, D, and then we need to compute the 6 lengths that represents. 4 points in space, 6 lengths, and I store the lengths in kind of a complicated data structure because I want to keep them A in order, and B, I want to keep the names of the point, or the edges actually. So AB is the edge from point A to point B and so forth. So I'm going from the apex, A to B, A to C, A to D, and then around the so-called base, CDB. It's important that when I use my volumes formula, I do enter the lengths in a specific order. Pick an apex, go down to the 3 corners of the opposite base, and then go around the base in the same order. So that's what I'm doing here. I'm creating a tetrahedron based solely on the lengths of the 6 edges entered in the order I just mentioned. That's all it takes, 6 lengths. And those lengths are not, look at that, those are not obviously whole numbers. Those are not rational numbers. Those are just arbitrary lengths, right, between the 4 points. So here we go. We create that tetrahedron, and now we ask for its volume in tetravolumes. The whole time this thing has been in tetravolumes. This Q-ray tetrahedron, not only does it have edges 1D or 2R, but it also has unit volume. And the volume computation that's going on with these 6 edges is going to spit back IVM volume, or unit volume is the tetrahedron. Tetravolume is the native method of this tetrahedron. That's what it does. And it will convert to XYZ volume. I'll show you that at the end. But that's not the native computation. So there we go. It's 8160888. And now in a demo, I just go back over what we just did and wrap it all up. In other words, pick 4 balls at random, compute the 6 lengths, feed that to your tetrahedron class, and return the volume. Do that all in one go. So we run demo, and we get back a whole number volume. Now sometimes, because of floating point, we're going to get like 0.99999 or something like that. So far it's been 0.0 every time, but we can't count on that. Okay, that worked. So another whole number volume. There you go. There's one of those 9999s. And we could extend precision and do Gimpy 2, as I've done in some demos. But for now, I think this is good enough. This shows you. So let's show you the XYZ volume corresponding to that tetrahedron. And this is where you have the usual unit cube of, edges 1, as opposed to tetrahedron of edges 2 having unit volume 2R. So that's not such a nice number, right? And Watermans are not whole number. It's like XYZ volume. We don't have as nice things to say about it in this curriculum as you're used to, right? So, all right, that's today's lesson. Enjoy. I recommend follow up with crystal ball sequence to get, if you're not up to speed on the packing we're talking about, and generating the FCC with quadray coordinates spelled out in much more detail in the same repository, 4dsolutions/Python 5. Check it out. All right, talk to you later.